Hello and welcome. The lecture that we are having today is about capacitance and capacitors. So what we want to understand is first to describe what capacitance is, and of course to know more about the material that holds them, which are of course capacitors. Then lastly, to solve problems that involves capacitance and dielectrics, which I will be explaining later. Capacitors, these are electrical devices constructed of two conducting parallel plates separated by an insulating material called the dielectric. So if you're familiar with this, so this is primarily seen on incandescent bulbs, the elongated one that you put in your dining area or something. So there's this cylindrical thing that you rotate, right? So that's what capacitor is. So there, so it can also be seen on circuit boards. So this is such an example. So as you can see, here are your capacitors. Alright, so capacitor stores energy in the form of an electric field that is established by the opposite charges on the two plates. So here are the characteristics. So in this case, I'm going to show you the formula first, and then we're going to discuss the characteristics. So the formula in writing the capacitance is C is equal to the relative permittivity of the material multiplied by the permittivity of free space multiplied by the area of the material, area on each of the side, alright, but you don't have to multiply it by 2, just one of the areas, then divided by the distance that is separating the parallel plates. Okay, so basically this is, so let's put a name on each. So this one is relative permittivity. Okay, permittivity there. Then this is permittivity of free space. I think we have discussed this on the previous topic, right? Okay, then we have this is the area. So this is very geometric again. Then this is the distance. Okay, so this area is very dependent on what type of, what's the measurement of the material that you are having. Okay, so if it is a square, it will be dependent on how are you going to obtain the area of a square, etc., etc. Then the distance, of course, this is just a given value or something that you can look for on the problem. So let's study the characteristics. So first, capacitance is directly proportional to the size of the plates. So that means the larger the area of the plate, the higher the capacitance, which makes sense. Okay, so they are both on the numerator side, so it means they are directly proportional. Next, capacitance is inversely proportional to the distance between the plates, which makes sense. If you remember the definition of capacitance and how it stores electricity or energy, so it's dependent on the electric field that is between the plates. Okay, so if you still remember the formula for electric field, of course you should remember that. So that would be kq over r squared, right? So as you can see, our distance in this case again is inversely proportional. So that is like a recurring theme in the concept of electricity. As you move further and further away from each other or from the source, in the case of electric field, the value gets smaller and smaller, or the strength gets weaker and weaker. So in the case of the capacitance, it's the same thing. Okay, then we have the dielectric constant. So the dielectric constant is this 2. So this is dependent on the material that you are using. Okay, so as you can see, we have 2 here, right? So epsilon sub naught, or the permittivity of free space, is the permittivity of the material when there's nothing in between them. So if these are your capacitive plates and the material that is only between them is the vacuum or air, the value of epsilon sub 0 is, the value of epsilon sub 0 is equal to that. So that's 8.85 times 10 raised to negative 12. Alright, then epsilon sub r is relative permittivity. So that means this is like, when you say relative, this is dependent on the type of the material. So like what I've said, if this is the value of the permittivity of free space, this one dictates what is the relative permittivity in relation to this. So if your material in between is air, so the value of this will be 1. Okay, so leaving you with a derived formula of capacitance, which will be epsilon sub 0 multiplied by the area divided by the distance. This is assuming, of course, that the permittivity, or the material that is separating the 2 parallel plates, is just a vacuum or air. Okay, because this will be equal to 1. Well, let's put this here. Is 8.85. Unit of this is, what's the unit? Coulomb squared per Newton meter squared, right? But you can rewrite this unit as well, okay, which I will be showing later. Okay, but I think oh, you can see later what would be like the final unit for this one. All right, so let's proceed. Next would be, again, capacitance is directly proportional to the dielectric. Okay, so the higher the relative permittivity of the material is, the higher the capacitance would be. So that means if you're going to place a material in between of these two, the value for the capacitance will be much greater. So if you're going to open, let's say, the capacitor that is attached on your light bulbs, you're going to see that it is separated by paper, the 2 parallel plates. If you try to open them, they are rolled in cylinder. Then if you lay them flat, you're going to see that there's a thin sheet of paper that separates the parallel plates. Next, we have the dielectric strength. So then we have capacitors always have dielectric, so that's what I've said earlier. Then lastly, we can note that a capacitor is at full capacity, or is fully charged, if the potential between the 2 plates is equal to the voltage source. So this will be further discussed, I think, on the next topic. For now, we're going to focus on the geometric properties of capacitors and how to obtain capacitance from them. So one of the key, or the major applications that we can find in, what do you call this, in modern technology on the use of capacitance and capacitors, are our smartphone screens. Okay, so our smartphone screens are very, very large capacitive, materials that are dependent on capacitance. Okay, so you can see it here. All right, so the difference in voltage when you touch the material, which is of course the touch screen, induces here. All right, when the finger similar to charged object touch the top glass, the electric field below it changes, so that registers as a touch. That's what happens. So then, of course, the measurement of the grids, which will be measured in x's and y's, okay, will of course, give the exact place where the touch is happening. Alright, so I think this could be further demonstrated to you by your teachers, or I could share a link that shows how this can be done. Alright, so yeah, just take note of the formula here. So this is like the formula that you have to remember. The relative permittivity will be given to in the problem, or will be provided by your teachers, unless it is the one being looked for. Alright, so without further ado, let's try to solve some problems. So we have here guided practice problem. So this is already what topic? 5th lesson, right? So this will be 5.1. Alright, so we have a capacitor that is made of 2 square metal plates with a side length of 3. So this will be easy because R square only has a side of 3 centimeters. So this is S is equal to 3 cm. Okay, and then there's a vacuum in between the plates, so this will be fairly easy. Then the distance between them is 1 millimeter. So if you're going to draw another plate here, something like this, and let's say this is the distance that separates them, I'm going to use yellow line. This is like a 3D representation. Okay, so let me show, or let me draw another one that shows the, what do you call this? How will they look if you write them, or if you draw them and showing the distance between the 2 parallel plates. So if you're looking at them from the side, so it will look like this. So let's say these are your capacitive plates, then this is the distance that separates them. Right, so let's have yellow. So this is like the distance that separates them, okay, which is similar to the drawing that we have here. Okay, so let's write our given. So for our sides, we have 3 centimeters, which is equal to 3 times 10 raised to negative 2 meters. Then we have the distance between the plates, which is what? 1 millimeter, which is what? 1, or let's just proceed with 10 raised to negative 3 meters, since that's basically the same thing. Then we have the permittivity of free space, which is 8.85 times 10 raised to negative 12 coulomb squared over Newton meter squared. And then the relative permittivity, which is vacuum, is 1. Okay, so let's proceed. Our required, of course, is capacitance. Okay, so don't make mistakes that this is C as in coulombs, okay? So that you will be very wrong when you do that. So for our equation, you have C equal to ER times EO times A over D. So our A here will be the area of a square. So this will be, then since ER is 1, we already can say that our formula for this problem will be permittivity of free space multiplied by area of the square. So that would be S squared from the given that we have, divided by the distance. Okay, so substituting, so you can have capacitance equal to 8.85 times 10 raised to negative 12 coulomb squared per Newton meter squared, multiplied by 3 times 10 raised to negative 2 meters. This is to be squared as well. then divided by the distance between them, which is what's that, 110 raised to negative 3 meters. So here you can proceed on cancellation. Alright, so for your final answer, your unit would be something in farads. Okay, so farads, of course named after Michael Faraday, is the unit for capacitance. Okay, so this can be also written as F. Okay, so something like that. Alright, so for our second guided practice problem for this topic, so we have the plates of a parallel plate capacitor are 7.28 millimeters apart and they're separated by neoprene rubber. So its relative permittivity 6.7. The plates are circular in shape with the circumference of 314 millimeters. So what is the capacitance? So in this case, our plates are drawn in circles. Okay, so you're gonna draw something like them. So it looks like this, which has a circumference of something. Okay, so the radius is not known yet. Okay, so if we're going to draw the distance between them, it will look something like this, assuming that we have aligned the centers perfectly, but don't mind it as long as you can imagine that these are parallel plates that are just circular in shape. So this is our distance. Okay, or I mean distance. So for our given, we have circumference, which is 314 millimeters, which is 314 times 10 raised to negative 3 meters. Okay, then we have the distance between them, which is 7.28 millimeters, which is of course 7.28 times 10 raised to negative 3 meters, correct? Next, we have a relative permittivity in this case. Okay, so according to the problem, this space is filled by neoprene rubber, which has a relative permittivity value of 6.7. Then lastly, you have of course the permittivity of free space, which is 8.85 times 10 raised to negative 12 coulomb squared per Newton meter squared. There. So for our required, we're tasked to look for, again, capacitance. For our equation, this is C is equal to ER E sub 0 A over D. Okay, so in this case, we're going to look for the area of the circle instead of using, of course, the given is circumference, but we need this area, so we got to look for it first. Okay, so let's derive for the formula of the area of the circle. So first, let's start with the circumference. Circumference is 2 pi r, right? So from there, to look for r, we just divide both sides by 2 pi. Okay, then you have r, which is of course c over 2 pi. Then you can now substitute this to the area of the circle. Substitute, I mean, which is pi r squared, right? So this will be pi multiplied by c over 2 pi to be squared. There. So you can break this down, so you can simplify it. So this just distribute, so you will have c squared over 2 squared pi squared, so you can cancel one of the pi. So finally you're going to have c squared over 4 pi is equal to the area of the circle. There. So yeah, you can now proceed on solving, since, or maybe you can substitute first. So finally you have the formula of ER, E sub 0, then you have e squared over 4 pi divided by d. There. Now you can substitute. So ER is 6.7 multiplied by 8.85 times 10 raised to negative 12 coulomb squared per Newton meter squared. Okay, multiplied by, what's our circumference? 314 times 10 raised to negative 3 meters. Okay, this is v squared, of course, divided by 4 pi. Okay, then all of this will be divided by the distance that separates these circular plates, which is, what's the value? 7.28 times 10 raised to negative 3 meters. So let's take a look again at the given 7. Okay, so there you go. So for the final answer, you will have something with the units of farads. Alright, so there. Now for the next guided practice problems, this will be further discussed to you by your teachers. Alright, and then that's it. Thank you so much, guys, and you have a good day. So on an extended note, I just want to add another equation that we can use on solving or finding capacitance, which will be based on how we define electric field and potential difference. Okay, so first let me rewrite this. Okay, so this is like the first equation that I have taught you. So for the second one, that would be C, or capacitance, is equal to Q over V. Okay, Q, of course, it stands for the total charge in the plates. Okay, then the second one will be, of course, the voltage. Okay, so this is the thing that I want you to remember. So you could see some beautiful equations that will arise from here. Alright, so remembering that voltage, defining it in terms of its potential gradient, is electric field multiplied by the distance. So you can show it by including it here on your the previous first equation that you have on this one. So you will be having C is equal to Q over EB is equal to I'm just going to simplify this now, so epsilon sub 0 A over D. Okay, so multiplying both sides, so you're going to have QD equal to ED multiplied by epsilon sub naught multiplied by A. So since you have distance on both sides, you can just divide them. Alright. And then, what else can we show? Here. So you can see the relationship here if you divide both sides by permittivity of free space. The first thing that you're going to notice is the formula for electric flux. So see the relationship of the following topics that we had. Okay, and then you can also show what else? Q. What did we learn from Q? We have voltage, we have potential energy. Oh, you can utilize potential energy as well. Alright, so since these are like different ways of expressing energy actually. Okay, so knowing that capacitance is total charge over voltage, and then you have potential energy, or energy is what? QV, right? So you can rewrite capacitance as Q over. So actually you can rewrite this as both capital Q, so we can no, there are different Q. This Q is the charge on the plates. This Q is the charge that you place on the uniform electric field that will experience the force. Anyway, so we're going to have Q over PE over Q, right? Which can be rewritten as P is equal to Q times Q over PE. Okay, so this will be P is equal to QQ over PE. Alright, so writing this in what do you call this? Units, you're going to see that QQ is what? Coulomb squared, right? Then this is joules, correct? Joules, and then knowing that joules is what? Can also be rewritten as this is C squared, then this is Newton meter to be squared. Is that correct? Or Newton meters, I mean. So this is a very familiar variable to you. So if you're going to show the cancellation of the units from this formula, so you have ER times E sub 0 times A over D, we will be arriving for this formula, which is the one of the derived formulas of Farad. Okay, so you can show it. Okay, let's just show it. So ER has no unit, so permittivity of free space is C squared over Newton meter squared multiplied by meter squared multiplied by meters. So there. So finally this is C squared over NM, which is Coulomb squared per joules. So I hope these relationships are making sense to you, as this will be helpful on connecting the topics that we have understood so far on since the beginning, electric force, right? So there you go.